In the vast, silent darkness of our own being, there lies a universe of staggering complexity. It is an intricate living landscape, sculpted over millions of years of evolution. This is the brain, a mere 3 pounds of tissue, yet it holds the entirety of our world, our memories, our dreams, and our very sense of self. It is the architect of our thoughts, the conductor of our emotions, and the silent engine that drives every beat of our heart and every breath we take. Within its folded valleys and dense forests of cells, the most profound mysteries of existence are played out every single moment. Today, we embark on an extraordinary journey, not across continents or oceans, but inwards, into the most remarkable structure known in the universe. We will explore its geography, from the great continental hemispheres to the deep, ancient structures that govern our most primal instincts. We will meet its inhabitants, the trillions of tiny, interconnected cells that communicate in a silent, electrical language, weaving the tapestry of our conscious experience. This is not just a story of biology, it is the story of us. Join me, Eve, as we venture into this hidden realm. We will navigate the pathways of thought, witness the birth of a memory, and marvel at the brain's incredible capacity to change and adapt. We will seek to understand how this astonishing organ makes us who we are, how it learns, how it feels, and how it perceives the world around it. The journey promises to be one of wonder, revealing the delicate, powerful, and beautiful machinery of the mind. Let us begin. Our journey begins with the physical structure, the magnificent citadel that houses the mind. It is, first and foremost, a fortress. Encased within the hard, protective shell of the skull, it floats in a clear, cushioning fluid, a moat of cerebrospinal fluid that shields it from the jolts and shocks of the outside world. Further protection is provided by 3 tough membranes, the meninges, which wrap the brain like a royal shroud. This precious organ, the command center of the entire body, is defended with the utmost security, for its delicate architecture is irreplaceable. The largest and most conspicuous part of this landscape is the cerebrum. With its deeply wrinkled surface, it is divided into 2 great hemispheres, the left and the right, connected by a thick bridge of nerve fibers called the corpus callosum. This is the seat of higher-order thinking, of language, reason, and voluntary movement. Beneath the great expanse of the cerebrum, at the back, lies the cerebellum, or little brain. It is a master of coordination, responsible for the grace and precision of our movements, for balance, and for the seamless flow of actions we perform without conscious thought. At the very base, connecting the brain to the spinal cord, is the ancient and vital brainstem. It is the life support system, tirelessly managing the automatic functions essential for survival: our heartbeat, our breathing, our sleep cycles. Tucked deep within the temporal lobes, we find the limbic system, the emotional core of the brain, governing our feelings, motivations, and the formation of long-term memories. And nearby, the basal ganglia work in concert with the cerebrum to initiate and smooth out the motions that allow us to interact with our world. Each part has its role, a specialist in a grand collaborative enterprise. If the brain is a kingdom, then its population is made up of billions of specialized inhabitants. The most famous of these are the neurons, the nerve cells. These are the primary messengers, the information carriers of the nervous system. Each neuron is a marvel of biological engineering, a tiny processing unit designed for communication. They are the stars of the show, but they cannot perform alone. They are supported by an even greater number of companions, the glial cells. Once thought to be mere glue holding the brain together, we now know they are active and essential partners. Glial cells are the tireless support crew. They provide nutrients to the neurons, they clean up waste products, and they form the myelin sheath, a fatty insulating layer that wraps around the long axons of neurons, much like the plastic coating on an electrical wire. This insulation is crucial, allowing nerve impulses to travel faster and more efficiently. Without the constant care and maintenance of the glial cells, the complex network of neurons would quickly falter and fail. They are the unsung heroes of the brain's ecosystem, ensuring the entire system runs smoothly. The structure of a single neuron reveals its function. It has a cell body, or soma, which contains the nucleus and the cell's genetic blueprint. Branching out from the soma are dendrites, intricate tree-like extensions that act as antennae, receiving signals from thousands of other neurons. A long single fiber, the axon, extends from the cell body to transmit signals outwards. At its end, the axon branches into terminals, which form connections or synapses with the dendrites of other cells. It is here, at these countless points of contact, that the story of the brain truly unfolds. The language of the brain is not spoken in words, but in whispers of electricity and chemicals. Communication between neurons is an electrochemical event of breathtaking speed and precision. It all begins with an electrical impulse, an action potential. When a neuron is stimulated enough by incoming signals from its dendrites, it fires. A wave of electrical charge, a brief, sharp spike of voltage, races down the length of its axon. It's a binary system, an all-or-nothing event. The neuron either fires completely or not at all, a single, clear note in a vast symphony. But this electrical signal cannot simply jump across the gap, the synapse, that separates one neuron from the next. To bridge this tiny chasm, the neuron must switch to a chemical message. As the action potential reaches the axon terminal, it triggers the release of tiny sacs filled with chemical messengers known as neurotransmitters. These molecules are released into the synapse and drift across the gap to the dendrites of the neighboring neuron. There, they bind to specialized receptor sites, like a key fitting into a lock. This binding event can have one of two effects. It can be excitatory, encouraging the receiving neuron to fire its own action potential, thus passing the message along. Or it can be inhibitory, making the receiving neuron less likely to fire, effectively dampening the signal. The brain uses a rich vocabulary of these neurotransmitters to modulate its messages. Dopamine is involved in reward and motivation. Serotonin influences mood and sleep. Acetylcholine is crucial for muscle contraction and memory. And GABA is the primary inhibitory messenger, helping to keep the brain's activity in check. It is the delicate and constant balance of these chemical signals that orchestrates the complexity of thought, feeling, and action. The great wrinkled expanse of the cerebrum is not a uniform landscape. It is instead a mosaic of specialized territories, each dedicated to a particular task. If we could peel back the skull and observe the brain in action, we would see different regions lighting up with activity depending on what a person is doing, thinking, or sensing. Running like a headband across the top of the brain are two parallel strips of cortex. The one towards the front is the motor cortex. This is the command center for all our voluntary movements. Specific areas within this strip correspond to specific parts of the body, creating a complete, albeit distorted, map of ourselves. Just behind the motor cortex lies its partner, the somatosensory cortex. This region receives and processes all the tactile information from our body: touch, pressure, temperature, and pain. Like the motor cortex, it contains a map of the body, with more sensitive areas like the fingertips and lips occupying a disproportionately large amount of cortical real estate. At the very back of the brain, in the occipital lobe, is the visual cortex. This is where raw signals from the eyes are transformed into the rich, coherent visual world we perceive. It deciphers shape, color, movement, and depth, constructing our reality from patterns of light. Tucked into the sides of the brain, in the temporal lobes, is the auditory cortex, dedicated to processing the sounds captured by our ears. It distinguishes pitch, volume, and timbre, allowing us to understand speech and appreciate the complexities of music. And speaking of speech, for most right-handed people, two critical language areas reside in the left hemisphere. Broca's area, located in the frontal lobe, is responsible for the production of speech, for forming the words we want to say. Wernicke's area, further back, is crucial for the comprehension of language, for understanding the words we hear and read. These specialized zones work in constant, seamless collaboration, a testament to the brain's incredible organization. A brain is not born fully formed. It is sculpted by a lifetime of experience. The journey begins in the womb, where a simple tube of cells burgeons into the complex structure we have been exploring. Neurons are born at a staggering rate, and they migrate to their designated locations, forming the rudimentary architecture of the brain. After birth, an explosive process of connection begins. A single neuron in a toddler's brain can form thousands of new synapses, creating a network of immense density. The young brain is a buzzing, highly connected jungle of possibilities, but more is not always better. To create an efficient and powerful mind, this dense network must be refined. This is achieved through a remarkable process called synaptic pruning. Based on an infant's experiences, the sights they see, the sounds they hear, the love they feel, certain neural pathways are strengthened and preserved, while those that are unused wither away and are eliminated. It is a use it or lose it principle on a microscopic scale. This careful sculpting is what tunes the brain to its specific environment, shaping the individual's abilities and inclinations. This ability to change and reorganize is not lost after childhood. It is a lifelong property of the brain known as neuroplasticity. Every time we learn a new skill, form a new memory, or adapt to a new situation, the physical structure of our brain changes. New synaptic connections are formed, and existing ones are strengthened or weakened. This living clay can remold itself, allowing us to recover from injury, learn new languages, or master a musical instrument even in old age. The brain is not a static, hardwired machine. It is a dynamic, ever-changing landscape, constantly being reshaped by the flow of life itself. Memory is the glue that binds our lives together. It is the archive of our past, the foundation of our identity, and the guide for our future actions. But it is not a single entity. We possess different types of memory, each handled by different systems within the brain. There is short-term or working memory, a temporary mental scratchpad that holds information for a few seconds or minutes, like a phone number we are about to dial. And then there is long-term memory, the vast storehouse of our knowledge and experiences, which can last a lifetime. Long-term memory itself has subdivisions. There is explicit memory, the conscious recollection of facts and events, knowing the capital of France or remembering what you ate for breakfast. This is largely managed by the hippocampus, a seahorse-shaped structure in the limbic system. Then there is implicit memory, which is unconscious and automatic. It includes procedural memory, the how-to knowledge of skills like riding a bicycle or tying your shoes, which is primarily handled by the cerebellum and basal ganglia. These memories are expressed through performance rather than recollection. The process of learning is the process of strengthening the connections between neurons. When we first learn something, the neural communication is weak and tentative. But with repetition and practice, the signal between the participating neurons becomes stronger and more efficient. This phenomenon is known as long-term potentiation, or LTP. The synapse becomes more sensitive, more neurotransmitters may be released, and the connection becomes more robust. In essence, learning carves pathways into the neural landscape. The more we travel a particular path of thought, the deeper and wider it becomes, making the information easier to access in the future. Memory is not a file in a cabinet. It is a pattern of strengthened connections woven into the very fabric of the brain. For centuries, sleep was seen as a passive state, a simple turning off of the body and mind. But we now know this could not be further from the truth. Sleep is actually a critical, active period for the brain, a time of honestly intense and vital activity. It is the mind's essential caretaker, performing crucial maintenance that is simply not possible during the waking hours. One of its most important jobs is house cleaning. Throughout the day, the brain's high metabolic activity produces toxic waste products, which, accumulate in the spaces between cells. While we sleep, something really remarkable happens. The brain's glial cells appear to shrink, increasing the space between neurons by as much as 60%. This allows the cerebrospinal fluid to flow more freely through the brain, acting like a plumbing system that flushes away these accumulated toxins, including beta amyloid, a protein linked to Alzheimer's disease. This nightly cleanse is absolutely essential for maintaining a healthy neural environment. Without sufficient sleep, these toxins can build up, impairing cognitive function and potentially contributing to long-term neurodegenerative disease. But sleep is not just for cleaning. It is also absolutely vital for the processes of learning and memory. During the deep stages of sleep, the brain replays the neural patterns of experiences from the day. This replay helps to strengthen the relevant synaptic connections and transfer fragile short-term memories from the hippocampus to the more permanent storage sites in the cortex. This is what we call memory consolidation. Sleep also helps to rebalance the brain's chemistry, resetting neurotransmitter levels and ensuring our emotional circuits are stable and ready for the challenges of a new day. So, far from being a waste of time, sleep is actually the foundation upon which a healthy, functioning mind is built. We are not merely thinking machines. We are, creatures of deep and powerful feeling. Our emotions, joy, fear, anger, love, are not random interruptions but essential components of our mental life, guiding our decisions and coloring our perceptions. The primary seat of our emotional world is the limbic system, that deep, ancient part of the brain. At its heart is the amygdala, a small, almond-shaped cluster of neurons that acts as the brain's alarm system. It's constantly scanning for threats and is responsible for initiating the fear response and linking emotions to memories. The limbic system does not work in isolation. It's in constant dialogue with the rest of the body through a master regulatory center, the hypothalamus. This tiny structure, no bigger than a pearl, sits at the base of the brain and acts as the crucial link between the nervous system and the endocrine, or hormone system. The hypothalamus controls body temperature, hunger, thirst, and fatigue, but it also translates emotional signals from the limbic system into physical responses by controlling the pituitary gland, the body's so-called master gland. When the amygdala sounds the alarm, the hypothalamus commands the pituitary and adrenal glands to release a cascade of hormones, chief among them cortisol and adrenaline. These are the stress hormones. They prepare the body for fight or flight by increasing heart rate, sharpening focus, and mobilizing energy reserves. Other hormones also play key roles in our emotional lives. Oxytocin, often called the love hormone, is crucial for social bonding, trust, and maternal attachment. The intricate dance between brain structures, neurotransmitters, and hormones creates the rich and complex tapestry of our emotional experience, a constant tide that shapes our inner world. We have journeyed through the brain's geography, met its cellular inhabitants, and observed its intricate mechanisms. Yet, we now arrive at the deepest mystery of all, the very summit of our exploration consciousness. How is it that the coordinated firing of billions of neurons, the release and reception of chemical messengers, gives rise to the subjective, private experience of being? How does the physical stuff of the brain produce the non-physical feeling of redness, the taste of a strawberry, the sound of a symphony, or the awareness of one's own existence? This is what philosophers call the hard problem of consciousness, and it remains one of the greatest unsolved questions in all of science. There is as yet no single, universally accepted explanation. However, a number of fascinating theories are being explored. Some propose that consciousness emerges from the sheer complexity and interconnectedness of the brain's neural networks. The integrated information theory suggests that consciousness is a measure of a system's ability to integrate vast amounts of information into a unified whole. Other theories focus on specific neural processes. The global workspace theory, for example, likens consciousness to a brightly lit stage in a theater. While countless unconscious processes occur in the dark backstage, information that becomes conscious is broadcast from this stage to a wide audience of specialized brain regions. These theories are not mutually exclusive and may each hold a piece of the puzzle. What is certain is that consciousness is not located in a single spot, but is likely a distributed network-level phenomenon, the ultimate emergent property of this astonishingly complex organ. The brain, for all its resilience and complexity, is a delicate biological organ. It's vulnerable to injury, disease, and the relentless passage of time. When its intricate machinery falters, the consequences can be profound, affecting every aspect of a person's life. A stroke, for instance, occurs when the blood supply to a part of the brain is interrupted, either by a clot or a bleed. Deprived of oxygen and nutrients, brain cells begin to die within minutes, leading to the loss of functions controlled by that area, such as speech, movement, or memory. Neurodegenerative diseases represent a slower, more insidious assault. In Alzheimer's disease, abnormal proteins, the plaques and tangles we saw being cleared during sleep, build up to toxic levels, leading to widespread neuron death, particularly in regions vital for memory and cognition. In Parkinson's disease, it's the dopamine-producing neurons in the basal ganglia that are lost, resulting in the characteristic tremors, rigidity, and difficulty with movement. These conditions gradually erode the very structures that support a person's identity. The brain's electrical activity can also go awry. Epilepsy is characterized by sudden, uncontrolled electrical storms in the brain, leading to seizures. And the delicate balance of neurotransmitters can be disrupted, contributing to mood disorders like depression and anxiety, which are not signs of personal weakness, but complex illnesses of brain chemistry and circuitry. Understanding these disorders is one of the greatest challenges of modern medicine. By studying what happens when the brain goes wrong, we gain invaluable insights into how it works when it is healthy, bringing us ever closer to finding effective treatments for these devastating conditions. Our journey through the inner universe reveals an organ of almost unimaginable power and intricacy. What we carry within our heads is far more than a biological computer. It's self-aware, capable of imagining, planning, and reflecting. It is the source of all art, all science, all love, and all sorrow. This 3-pound mass of tissue generates the totality of our reality, a private, subjective world of breathtaking richness. And perhaps most remarkably of all, through the property of consciousness, it is the means by which the universe itself has become aware of its own existence. The brain is not a static entity fixed at birth. It is a dynamic, living structure that is constantly changing. It can change itself with learning and experience, forging new pathways and adapting to new challenges throughout our lives. This capacity for change, for plasticity, is the biological basis for all growth, all recovery, and all hope. It means that we are not passive passengers in our own lives, but active participants in the sculpting of our own minds. Every book we read, every conversation we have, every new skill we acquire physically alters the landscape of our brain. We stand at an incredible moment in history. We are just beginning to unlock its mysteries through neuroscience, AI, and brain-computer interfaces. The map of the mind is being drawn with ever-increasing detail, and the secrets of its function are slowly yielding to our inquiry. The journey to fully understand the brain is perhaps the final frontier of human exploration. There is so much more to discover, so much more to learn. If you've been fascinated by this exploration into the organ that makes us human, please like this video and subscribe for more.